is negative temperature coefficient. In case of metal, what happens if we increase temperature, the vibration increases, and due to vibration it is very tough for us to move the electron from one place to another. So all type of metal normally they are having positive temperature coefficient. अगर आप temperature बढ़ाओगे तो resistance बढ़ेगा. But in case of semiconductor, the funda is different. Semiconductor is having covalent bonding, and all the covalent bonding, all the electrons there, they are in valence band. We need to bring them to conduction band for movement. So temperature, this temperature, it will help you to break the covalent bonding and bring the carriers from valence band to conduction band. So if you increase temperature, obviously number of carriers will increase, number of bonds will be more broken. So as temperature increases, number of carrier will increase, so its resistance will decrease. So when temperature will increase, its resistance will decrease. So that is the definition of negative temperature coefficient, as I told. So our answers will be a semiconductor has negative temperature coefficient. Next is question number 3. The most commonly used semiconductor is, I told in the class, silicon. Because readily available in the market. Yeah.
Stability, sir. Highly temperature stability.
Stability of germanium is also good. Stability of gallium arsenide is also good. But silicon is plentifully available in form of silica. हमको जो समुद्र में बालू मिलता है, that is silica. So that is very hugely available in nature. As it is hugely available in nature, its cost, production cost is very less. You can see in the lab how many diodes we have taken from there. All diodes are having threshold voltage or floor voltage around 0.7. So all are silicon diode. Silicon diode cost is 20 paise, whereas germanium diode cost is 10 rupees. So it is due to the availability of silicon only. As silicon is plentifully available, that's why its production cost is very less. That's why the most commonly used semiconductor is silicon. So next, a semiconductor has how many valence electrons? We know it is 4.
Four.
All sir. Yeah. All semiconductors are group 4 material, so they are having valency 4. Resistivity of pure germanium, you can see how values they have given. 10 to the power 4 ohm semi, it's the order of resistor, so it's not semiconductor. 10 to the power 6 ohm semi, it's more resistor, very high value of resistor like wood. 10 to the power minus 4 ohm semi is of conductor. So our answer will be this, 60 ohm centimeter. It's between the insulator and conductor. Resistivity of germanium is about 60 ohm semi, and next question, resistivity of silicon is around 6000. Germanium is more conductive than silicon. In silicon, at room temperature, number of carriers are 10 to the power 10 per centimeter cube. That is the intrinsic carrier concentration. Whereas in germanium, it is 10 to the power 12. So germanium is more conductive. And as I told, 10 to the power 10 and 12, this is around 100 times. Silicon resistivity is 100 times more than germanium. The resistivity of pure germanium is, remember, around 60 ohm centimeter, it's 58 point something. The resistivity of pure silicon is about 6000 ohm centimeter. It's around 100 times of germanium. Next question, when a pure semiconductor is heated, just now I have told you,
goes down.
Semiconductor has negative temperature coefficient. So temperature बढ़ाएंगे तो ये घटेगा. So when a pure semiconductor is heated, its resistance will goes down. So this answer will be goes down. The strength of a semiconductor crystal comes from forces between nuclei, forces between protons, electron pair bonds, none of the above. We know silicon or any semiconductor its force is its covalent bonding only. It depends how much strength it is having in the bond. Depending on that, the energy required to move into the break the bonding. Now for silicon, energy required to break this bonding is 0.7 volt. For germanium, it is 0.3 volt. For gallium arsenide, it is 1.1 volt. So only this bond, this bond decides how much strength is required to break this silicon bonding. So this is actually the covalent bonding or electron-electron bonding or electron pair bonding. So the answer will be either electron pair bond, or you can write if sometimes they may write covalent bonding also. So it may be like this answer also they may give. The meaning is same. So the answer will be electron pair bonds or electron-electron bonds or covalent bonds. So our answer will be this. So next question, when a pentavalent impurity is added to a pure semiconductor, it becomes an, so pentavalent impurity it is added means a semiconductor is having 4 valency. When a pentavalent impurity is added, 4 will make 4 hands, 1 electron, penta means 5. 1 electron will be extra. So jitna pentavalent impurity will impure, that many electrons will be extra. So semiconductor will have electrons extra. So semiconductor will become N-type semiconductor. So this will be the answer. We know to make N-type semiconductor, pentavalent impurity is required. To make P-type semiconductor, trivalent impurity is required. Addition of pentavalent impurity to a semiconductor creates many free electrons. So jitna pentavalent impurity डालोगे, that many free electrons will be generated. So addition of pentavalent impurity to a semiconductor creates many free electrons. The pentavalent impurity has 5, that we know 5 valence electrons. And N-type semiconductor, any semiconductor, as inside the semiconductor there is number of electrons and number of protons, they are same. We cannot take out from the complete semiconductor. So as I told, any time through force we are moving from one part to another, but ultimately the number of electrons and protons remain same. So any semiconductor, that will be N-type or P-type, they are actually electrically neutral. Electrically they are not having any charge. So the answer will be electrically neutral. A trivalent impurity, same way we can say a trivalent impurity is having 3 valence electrons. Pentavalent is having 5, so trivalent is having 3. Addition of trivalent impurity to a semiconductor, many holes. The hole in a semiconductor, we know hole is not a particle. Hole means there is a free space, scarcity of electrons. This is the bonding.
The incomplete part of an electron pair bond.
Yes. So in this bonding, if a electrons will be removed from here, then a hole is created. So hole means a void space or a free space. Always same answer will be not written. So you have to understand the answer. Answer will be the void space or the free space. Here the answer is written as incomplete part of the electron pair bond. So here this will be the answer. In this question, as per the answer given, this is the most suitable answer. So next question 16. The impurity level in an extrinsic semiconductor is about dash of pure semiconductor. So it cannot be it's because you can add any type of impurity starting from 10 power 10 to 10 power 23. We know depending on the applications. If it is crystal diode, impurity is less. If it is Zener diode, impurity is more. For transistor, for emitter, base, collector, different impurity. So this question is wrong. Cannot answer this question. Depending on the applications, it may be anything. Starting from 10 power 10 to 10 power 23. Impurity cannot be less than 10 power 10. Impurity cannot be more than 10 power 23. So these two margins I have told in the class. Inside these two margins, it may be anything. Now 17. As the doping to a pure semiconductor increases, the bulk resistance obviously doping बढ़ाने से carrier बढ़ेगा, resistance घटेगा. So if we increase doping, number of carriers will increase. So obviously resistance will decrease. So resistance will decrease will be our answer. A hole and an electron in close proximity as they are opposite charge. Hole is positive charge,
attract each other.
Yeah. So they will attract each other. They will attract each other. So next question, in a semiconductor, current conduction is due to, I told you in class, semiconductor is a bipolar material. Here current conducts due to both electrons and holes, not a single element. So here current conducts due to holes and electrons, not a single thing. The random motion of holes and free electrons due to thermal agitation. So I told due to potential gradient, the movement of carriers are called drift. Due to concentration gradient or any other gradient, if the carrier moves, then that phenomena is called diffusion. So here the answer will be diffusion. टेम्परेचर को अगर बढ़ाओगे या घटाओगे, जो इलेक्ट्रॉन मूव करेगा वो प्रोसेस को डिफ्यूजन बोलते हैं. या कंसंट्रेशन, इफ यू चेंज द कंसंट्रेशन आल्सो, carriers will go from high concentration to low concentration area. That phenomena is called diffusion. So next questions will go. A forward biased PN junction has a resistance of the order of, if you have remembered the forward bias characteristics what you have done in lab, you have made and some
converted to kilo ohm.
No, not kilo. VD and ID. This is resistance of diode. This is not the resistance of load what you have connected. So VD and ID you have measured, no? So you have got starting at 0.4 volt, maybe 0.4 volt. VD you have got in volts. ID you have got in milliampere. The current you have got around 0.1 milliampere, like this. And at some high voltage like 19 volt or 20 volt, forward voltage
19.74 km.
Forward voltage, if we are saying, it will not be that much. Maximum you may get 0.67. So there you may get current 19.3 or 19.4 like this, not more than this. This much current you have got in lab. So forward bias resistance of the PN junction, small rd, is equals to 26 millivolt by ID. This formula we have established. So here ID you can see ranges from some 0.1 milliampere to 19.4 milliampere. Till in this range it will vary. So RD will vary. Suppose ID is 19.4 or something. So milli cancel. It will be some 1 point some volt by ampere equals to ohm. So the range will be ohm only. R will be measured in volt by ampere. So it is ohm. In the reverse bias, if you see, in the reverse bias, current is IR. IR is in microampere. In forward bias, it is in milliampere. Reverse bias, microampere. So that time this RD equals to 26 millivolt by some microampere. Now milli means 10 to the power minus 3. Micro means 10 to the power minus 6. This one it will go to top into 10 to the power 6. So here it will come some 26 into 10 to the power minus 3. बस ये जब ऊपर जाएगा into 10 to the power 6 हो जाएगा. So this will be some 26 into 10 to the power 3 ohm. 10 to the power 3 माने kilo. We know 10 to the power 3 means kilo. So it will be in kilo. So in forward bias, the range is ohm. In reverse bias, the range is kilo ohm. This is diode resistance. So a forward bias PN junction has a resistance of the order of ohm. Next, the battery connection is required to forward bias PN junction. We know forward means P with P and end with N.
Positive
So,
to P.
positive with P and negative with N. This will be the answer. The barrier voltage of a PN junction for germanium, we know for so many times we have told, for GE or germanium, it is 0 barrier potential or threshold or knee voltage is 0.3. For silicon, it is 0.7. For germanium, for gallium arsenide, it is 1.1. So these three only will remember. For germanium 0.3, silicon 0.7, gallium arsenide 1.1. So this is the question here is for germanium. So answer will be 0.3. Next question, in the depletion region of a PN junction, there is a shortage of depletion region. If you have remember, depletion region is a junction of P and N. यहाँ पे क्या होता है? Here जो plus and this side minus, they will recombine and ये junction में और carrier नहीं रहता है. So at the junction there will be only immobile or fixed ion silicate. There will be no carriers. So in the depletion region of PN junction, shortage means कमी है. इसका कमी है carriers. So carriers are holes of electrons here. So in the depletion region of a PN junction, there is a shortage of holes and electrons. Here this will be the answer. Next, a reverse bias PN junction has very narrow depletion layer. No. For reverse bias PN junction, depletion layer will be more. Almost no current. Yeah, this is correct. Very low resistance. No. Reverse bias is having high resistance. Large current flow. No. Current flow is very less. So second one is the answer. Almost no current. A PN junction acts as a control switch.
Unidirectional switch.
Unidirectional switch. None of the above. I told PN junction is a unidirectional switch. Yeah. If the pressure and the arrow direction matches, pressure is from this side to this side, current will flow. Pressure and arrow direction is opposite, current will not flow. So it allows the current in one direction only. That's why the device is called unidirectional switch. So this is unidirectional switch. Next, a reverse bias PN junction has resistance of the order of kilo ohm. Just now.
Kilo.
Yeah. The leakage current across a PN junction is due to minority carrier. Forward current is due to majority carrier. Leakage current is due to minority carrier. Leakage current means reverse current, reverse bias current. When the temperature of an extrinsic semiconductor is increased, the pronounced effect in capacitance we haven't taught yet. So after teaching, we will understand this. What is the effect on capacitance? With a forward bias to a PN junction, the width of a depletion there, we know in forward bias, width will be reduced. So it will decrease. The leakage current in a PN junction means reverse current. It is in microampere range. So the answer will be forward current is in milliampere, reverse current is in microampere. So microampere option is right. In an intrinsic semiconductor, the number of free electrons, intrinsic we know intrinsic में N and P समान रहते हैं. The bonds are broken and due to broken bonds, the carriers are generated in pair. Number of electrons and number of holes are same. So the first answer is correct. The intrinsic means pure.
Number of holes.
Intrinsic means pure. In a pure semiconductor, the number of free electrons equals the number of free holes. दोनों का मान same होता है. At room temperature, an intrinsic semiconductor has many holes only, a few free electrons and holes, many free electrons, no holes. Obviously, at room temperature, there will be free electrons and free holes, but the number is less. So the answer will be a few free electrons and holes. The number is less. A few will be there, not many. At absolute temperature means at 0 degree Kelvin, number of electrons will not be there because the structure is complete now, no bonds are broken. So at absolute
No
temperature,
holes or free electrons.
no free holes and electrons will find at that time. At room temperature, an intrinsic silicon crystal acts approximately as number of carriers are less, it will act like an insulator. In very high, after very high doping, it will act like a conductor, but at room temperature, an intrinsic pure semiconductor acts like an insulator. So here the answer will be an insulator. So here in this chapter, this many questions are there we have discussed. We'll go to next chapter. Before that, anybody is having any doubt in these questions, you can ask. So now we will go to the next chapter. Chapter 6.